Swayam Prabha. Digital India. Educated India.
Okay, so good morning, good afternoon. Welcome back to our series of lectures on analysis and design of rigid pavements. We have been in module 2, which is the analysis of rigid pavements using classical methods. Now, just as a reminder, when we say classical methods, we basically mean old methods, but what that specifically means is these are methods where we get closed analytical solutions, solutions which we can solve by hand, maybe with a calculator, at most with a spreadsheet software, but solutions which don't require any sophisticated computer programming. Those are what we call classical methods. So, in this module on analysis of rigid pavements, we have mainly only looked at JPCP, that's jointed plain concrete pavements. I remind you that there are basically four types of rigid pavements. That is JPCP, which I already defined, JRCP, jointed rigid concrete pavements, CRCP, continuously reinforced concrete pavements, and PCP, pre-stressed concrete pavements. So PCP and JRCP are specialized applications. In fact, JRCP is rarely used anymore. So we're not going to discuss them in the class. In module 2, we have mostly been looking at JPCP. CRCP will come across again in module 4 actually. So it'll take a little while for us to reach CRCP. But there you'll see that mostly the design is fairly similar to JPCP. So that's why we're not going into too much detail over CRCP at this point of time. So, within this module 2 of JPCP, we have been looking at a couple of different things. We have been examining how to analyze when loads are placed on slabs. So, we were introduced to the very celebrated solutions of Westergaard, which are based on plate theory, in particular the Sophie-Germain equation, sitting on top of a dense liquid foundation or a Winkler foundation. We saw some analytical solutions for that. And then we looked at Freiberg's theory for the analysis of dowels, where again we looked at certain analytical solutions to estimate the bearing stresses, as well as an empirical formula for the allowable bearing stress that a dowel would have on a slab. Now, what we've been doing recently in the last 3 lectures, we've gone through a series of lectures on the effects of climate on the performance of JPCP pavements. Now, when I say climate, we discussed what climate means and the various aspects of it. Specifically, I talked about the effect of temperature and moisture. So, within temperature, as we discussed, we have non-linear temperature distributions. And then we saw what type of stresses they develop inside JPCP. When we talk about performance of JPCP, to an extent, we are concerned with the stresses which are developed inside the pavement. As we move into module 4 later, we'll put some more definiteness to it and start examining what performance really means from an analysis and design perspective. But for now, you can say performance is sort of a way of saying stress. Now, we looked at the effect of temperature, and then we also looked at the effect of moisture. In moisture, I said there is the long-term effect of moisture, which is basically flooding or when you have a large amount of ponding on the pavement. And we showed there that there's, as such, we don't analyze it, but mostly we make sure that it doesn't happen. So it requires a good amount of maintenance to make sure that there's no ponding, and even if if there is ponding, it doesn't significantly affect the JPCP performance. What we were particularly interested though is short-term or early age behavior when we have shrinkage cracking. That's happening because of the development of a moisture gradient. So not a temperature gradient, but a moisture gradient in a very thin segment just in the upper part of the JPCP slab. And those moisture gradients lead to the development of fairly high strains, which can in turn lead to development of cracking if we don't have any control over it. So these are the concepts we looked at last time. Now, what I realized is over those 3 sets of lectures, we actually went through a lot of formulas, we went through a lot of new concepts, but I didn't show you how to solve any particular problem. And since we are on the topic of classical methods, it's still very much possible to solve these problems by hand. We don't need a computer or a sophisticated computer program to solve this by hand. So today's lecture objectives are to calculate the equivalent components of a nonlinear temperature distribution. I'll give you an example of a nonlinear temperature distribution, and we'll go through all the steps required to actually calculate its equivalent components. So as a reminder, what do we mean by equivalent components? If I have a JPCP section and I measure the temperature, it can be measured with a thermocouple, for example. I measure the temperature distribution, it might be something of this sort. As always, we are not exactly interested in the actual temperature distribution. We are actually interested in the temperature distribution with respect to some reference temperature T naught. It doesn't really matter what T naught is finally to our calculations, as we shall show. It's quite common to just take it as 0 degrees Celsius. It's perfectly fine. Okay, so we have this, and then as I had mentioned, this can be decomposed into three components. So there is a constant component. This constant component essentially causes expansion and contraction. But as we said, that unless there is a significant amount of friction from the base layer, which is seldom the case, the base friction is usually very small. So unless there's a significant amount of friction from the base layer, we don't have too many stresses or very high magnitude of stress coming out of this component. And so usually we assume that the stress from this component is negligible. Then this can be decomposed further into a linear temperature distribution, as I've drawn over here. Now, the linear temperature distribution, on its own, it doesn't cause any stress. It just causes the pavement to curl. So either it takes a shape like this or it takes a shape like this. It causes the pavement to assume this sort of a shape. However, under any restraint, the pavement is not able to assume this shape that it desires. And that restraint is actually what causes the development of what we call curling stresses, which are right over here. So what we call curling stresses, that's called by a restraint to this sort of a strain. So the curling stresses, what are the possible restraints? Obviously, if we have a load, as I've drawn over here, so if we have a load that is preventing the pavement from taking the shape, that's a restraint. There's also the self-weight. The slab is not weightless. The slab actually weighs quite a lot. You would individually none of us would be able to pick it up. So it has quite a lot of weight, and that weight itself causes some amount of restraint. So this linear component, because of the restraint and because of the external load, it causes a certain amount of stress. Now, we did not see how to actually calculate this stress, taking both the temperature distribution or the temperature difference, delta T, which I remind you is the T top minus T bottom temperature. We do not actually see how how the stress can be calculated. For that, we'll actually have to go to the finite element method in module 3. So we'll keep that aside for later. What we also saw that there is a third component. So if you do this decomposition, you'll still be left with a little bit of a residual temperature distribution. That residual temperature distribution, which might look something like this, as I've drawn over here, this is the non-linear temperature distribution, and it leads to development of a certain stress, which has three different names: self-equilibrating stress, non-linear stress, or eigenstress. And eigenstress is sort of the more mechanistic term. From mechanics, it makes the most sense. Self-equilibrating comes from the fact that this is the stress that is keeping a plane section which was plane before bending as plane after bending. So if you recall, that was one of the assumptions we made in the medium thick plate theory. And it has been shown that that theory works very well in predicting the performance of slabs. And so that's why we know that this additional residual stress is indeed present, and we have to take it into account as well. So we learned that this non-linear temperature distribution leads to all three effects. And so given a non-linear temperature distribution, we have to know how to be able to decompose it so that we can go on to calculate the stresses. All right, the other thing we studied was the equivalent shrinkage temperature distribution. So we saw that when we have shrinkage, then we might have a we might have a strain distribution, something of this sort. So we have a very high strain at the top, and at some depth, HS, so some depth of shrinkage, it goes to zero. And then below that, we are basically at saturation, so we do not have any shrinkage strains forming. So we saw for this type of a triangular distribution, we have some shrinkage strain epsilon SH, and we saw that we generally write this as some alpha TSH, where alpha is the coefficient of thermal expansion, and TSH is some sort of equivalent shrinkage temperature. So it's a fictitious temperature, but we just call it a temperature that creates the same strain as the shrinkage. And so that's the value that we assume on the top over here. And then we perform the same analysis here. So this is a piecewise linear temperature distribution, or a strain distribution, if you may. So this is a piecewise linear temperature distribution, and it can once again be decomposed into these three components. And we saw the formula for doing that in the previous lectures. So what I'm going to do today is we're going to go through two examples where we will look at how each of these problems can be solved. The purpose of it is, of course, to show you the process by which you can solve these so that you can do it yourself by hand. but it's also to comment a little bit on the magnitude. So you should have a sense of typically what do these results look like for a realistic pavement case, so that you can actually check whether your answers are correct or not without knowing the correct answer per se. So it's not just a question of being able to calculate the answer, it's a question of being able to judge whether the answer looks correct or not. Okay, so just as a quick recap, I had already mentioned this, so I'll quickly run through this. We looked at what are the different factors affecting the temperature distribution in JPCP slabs. The same concepts apply to CRCP. So I didn't say it explicitly, but we can use the same principles for CRCP as well. We saw how this nonlinear temperature distribution can be decomposed into its three components. And we looked at the Bajant and Voyager B3 model for shrinkage. That's a very popular model that's used in pavement applications. There are other models also, which we saw in the ACI 219 document. But generally, we prefer to use this model for pavement applications. So we looked at all this, and now it's time to actually solve some examples using these concepts. Okay, so here is our first solved example. Here we go. So a JP Sleepy slab of 200 thickness. As usual, as you're reading the example, it's very important that you highlight what are the variables and very importantly, what are their units. So in this case, we're going to perform a temperature decomposition. As we perform a temperature decomposition, we know that what's very important is the thickness as well as the temperature. So we can choose temperature to be degrees Celsius. We could choose it to be degrees Fahrenheit, we could choose it to be Kelvin. It doesn't really matter as long as we stick to a uniform choice. So we choose temperature to be in degrees Celsius and we choose thickness to be in millimeters. So in particular, we're given that the total thickness of the section H is equal to 200 Now, given that this particular slab has thermocouples embedded in it, so what would typically happen is if this is a slab, as an engineer, if I wanted to measure this, I would go out, I would actually core a little bit of the concrete out, and then I would attach on the side surface, on the walls over here, I would attach these thermocouples. So a thermocouple, for those of you who've never come across this term before, it's simply an instrument which measures temperature. So its resistivity is actually proportional to the temperature. So you pass an electric current through it and it has been pre-calibrated. So when you pass a given electric current through it, and then you measure what is the electric current on the other side, so you can measure the loss in voltage. When you measure the loss in voltage, that has been calibrated to be proportional to the temperature. So based on the voltage loss, we can use the calibration coefficient and calculate the temperature. That's how a thermocouple works. Generally, they're not very expensive instruments. It's quite simple to perform this, and it is done in many cases. So we attach these thermocouples to these walls, and then we measure a certain temperature. So again, this H is 200 So what's given here is in this table, depth from the surface in millimeters versus the temperature measured by the thermocouple. Now, of course, it's obvious that this temperature is going to change during the day. As the position of the sun moves, where it might become cloudy, the wind might change, etc. Depending on all these weather factors, the actual temperature distribution will change. So you should read this as this is a snapshot at a particular point of time in some pavement somewhere on the planet. Somebody's gone out and measured this. It's not meant to be some kind of a universal number that all pavements at all times will have a distribution like this. Okay, so given at 25 we have a temperature of 52.5 degrees Celsius. Now, once again, you should pause and think, does this seem like a reasonable number? So in India, as you know, in summer, we can get 40 plus degrees Celsius. It's not unusual in many places. The surface temperature can easily be 10 degrees Celsius warmer than air temperature. That's actually quite a common observation. You yourself can actually go out and measure it, but be careful if it's a hot day. So let's say the air temperature during a hot summer day is maybe 42 degrees Celsius, not an unusual phenomenon. And so the surface temperature could be 10 degrees above that. That's quite normal. In fact, if you have flexible pavements, you can be even at a higher temperature than even that. But since it's a rigid pavement, it has a higher albedo, the temperature is a little bit lower than what you would get with a flexible pavement. So on the face of it, this seems like a reasonable number, that it's 52.5 degrees Celsius, not exactly at the surface, but this is at 25 and we'll discuss that in a second. Okay, given that another 25 below that, at 50 it has a lower temperature of 50.5 degrees Celsius. So about 25 below the first thermocouple, we saw a reduction in temperature of about 2 degrees Celsius. At a depth of 100 the temperature was measured to be 46.3 degrees Celsius. At 150, 44.2 degrees Celsius, and at 175 mm, 43.1 degrees Celsius. So, the first of all, what we can see, we will plot this graph in a second, but what we see is the temperature at not at a surface, but just below the surface is the highest, and the temperature not at the bottom, but just above the bottom is the lowest. So the temperature is going from a high temperature to a low temperature as you go into the depth of the pavement. As we had this discussion in one of our previous lectures, you can imagine that this temperature distribution was probably taken during the day. That is, the top surface is warmer than the bottom surface. That's typically going to happen during the day. So this might correspond to some sort of daytime temperature as it's been measured. Now, one thing to note, which I've put down here also, the thermocouples are not provided at the top and bottom surfaces due to practical limitations. This, I think, is fairly obvious if you actually imagine yourself attaching the thermocouple exactly at the surface. It's difficult to attach the thermocouple because the thermocouple has a finite length. It's very difficult to put it exactly on top. Furthermore, due to practical reasons, you don't want someone accidentally stepping on the thermocouple or any vehicle going on the thermocouple, etc. So you generally don't want to keep the thermocouple right on the top. You put it a little bit at a lower position. Similarly, at the bottom, if at H is equal to 200, you actually have an interface with the base layer. So it's very difficult to attach the thermocouple exactly at the interface. Most likely a mistake is going to be made, or the thermocouple will be damaged in the process. So that's why at the very bottom of the pavement also, we generally do not place the thermocouple. So that's why you'll see the first thermocouple is at 25 mm and the last thermocouple is at 175 mm. So these are a little bit short of the total depth of the pavement, and that's fine. That's actually quite normal. Okay, so given all this data, we are asked to do the following. First, obtain a best fit approximation of a quadratic temperature distribution. So if you recall from our previous lectures, there was a study by Tia and Kobane where they showed that to a large extent, you can pretty much approximate the temperature distribution through the JPCP using a quadratic distribution. Now, there are other ways to do this also, and we'll talk about a little bit towards the end of this example. But to a large extent, a quadratic distribution is generally not a bad assumption. So that's why we're asked here to create a best fit approximation of a quadratic temperature distribution, and then to calculate the equivalent components of the non-linear temperature distribution. So we are asked to decompose this T of Z, which is given in the previous slide. We are asked to decompose it into TL of Z, which is the linear component. Before that, TC of Z, which is the constant component. And then Tn of Z, which is the non-linear component. And from the non-linear component, we are asked to calculate the maximum tensile eigenstress. So those are the three questions that we've been posed in this problem. Okay, now what we're going to do is we're not going to reinvent the wheel. We are not going to rederive all the formulas which we had last time. I do encourage you to do the derivation when you go through that lecture. But having done the derivation, we don't want to do it again. Instead, we're simply going to use the formulas that we showed in the previous set of slides, which came from that paper which I had shown you back then. Now, one thing to note that in the data which we're given over here, this is the depth Z. This is going from 0. So technically it starts at 25, but that means it's starting from the top. So it's going from 0 to H. H is 200, although we don't have a thermocouple exactly at H, but that's the order in which this is going. So in the given data, Z, which is the depth, is actually shown from 0 to H. But if you recall the previous slides, we had taken Z to be 0 at the neutral plane and increasing downwards. In other words, our given coordinate system is that Z is up here and pointing downwards. Whereas the coordinate system in the formulas that we developed was that at a depth of H over 2, which is for a plane stress for a plane section, that is where the neutral plane is. At a depth of Z over 2, the H over 2, that's where Z begins and points downwards. So we have to perform a coordinate transformation in order to convert from the given coordinate system to the coordinate system for which we have a series of formulas. We could avoid doing this, by the way. We could rederive all those formulas because a coordinate system at the end of the day is an arbitrary choice. So it's not that we are stuck with one coordinate system. But because the formulas have already been derived, shifting a coordinate system is a relatively easy process. We generally don't want to change this coordinate system. So what we'll do is we need to perform a transformation on our original coordinate system to get to our new coordinate system. The transformation is very simple. What we have is in our given coordinate system, the neutral plane is at z is equal to h over 2. And then in the required coordinate system, the neutral plane is at z is equal to 0. So all we have to do is we have to take our original data, let's say it's z, and we subtract h over 2 from it. So what will happen when we subtract h over 2 from it is that the neutral plane, which in the given coordinate system is at h over 2, will now become at z is equal to 0, which is exactly what we wanted. So we perform this transformation that z is equal to z minus h over 2. That is basically going to shift our coordinate system to the neutral plane, which is what our formulas were based on. So when we do that, we get this data over here. Now, I should add h is given to be 200. So properly speaking, z should go from minus 100 to 100 in our transformed coordinate system. But because in the top 25 mm and bottom 25 mm, in that area we don't have a thermocouple, our z coordinates as given for this distribution actually goes from minus 75 to plus 75. But keep in mind, these are the values of z for which we have the temperatures, but the actual z goes from minus 100 to plus 100. And we'll see the application of this in the next slide. The temperature distribution stays exactly the same because after all, it's just a coordinate transformation. We are changing the coordinates of our points. We're not changing the values of the temperature at those points. So physically, the points are still where they are. We are just doing a coordinate transformation. So after we do this coordinate transformation, we can now answer the first question, which is, how can you fit this to a quadratic expression? Now, this class is, of course, not a mathematics class. I assume all of you have taken some amount of engineering mathematics and you know how to fit a curve. You can do it by hand. It's not extremely difficult, but it's not very usual to do it by hand. What's more common is to do it on a computer program, for example, Excel. So here what I've done in Excel is I've actually plotted these values. So what I've done is I've plotted Z, which is from the mid plane on the x-axis, and on the y-axis I've plotted those temperatures, which I showed in the previous graph. And these circles over here, they represent the given values. And then I asked Excel to give me a best fit for a second degree polynomial. And that's the equation which I get out of here. So for this, again, the values we have are from minus 75 to 75. So to go from minus 100 to plus 100, there's a little bit of an extrapolation involved. So we have to take that factor into account, that we are doing somewhat of an extrapolation beyond the given data. It's inevitable because it's very difficult to put the thermocouple at exactly the surface and exactly at the interface with the base layer. Okay, so after we do this, Excel will give us a best fit line, and Excel will actually give us the equation for the best fit line also. So because we asked for a quadratic distribution, the equation, which I had also shown last time, is going to be of the form T of z is equal to a plus bz plus c z square. And so this is the corresponding best fit curve that we get. You will also note the r squared, and I hope you remember r squared is called the goodness of fit. So the goodness of fit here was r squared is equal to 0.9975. The way to interpret this number is that if we assume our data is varying quadratically, it's an assumption which you're making, but if we make that assumption, then what r squared of 0.9975 says is that 99.75%, almost everything, so 99.75% of the variation in our data can be explained by a quadratic distribution. Remaining 0.25% can't be explained. So maybe we could have used something of a higher order polynomial or some other way in order to get a better fit. But in general, 99.75 for engineering applications is more or less everything. The remaining 0.25% can simply come from a little bit of experimental error here and there, which we are generally happy to live with. So what we have in this case is r squared is equal to 0.9975, extremely good. So we accept this temperature distribution as our best fit quadratic temperature distribution, again with the idea that we are doing a little bit of extrapolation for the first 25 mm and the last 25 mm where we don't have any data. Okay, so what we get is, to summarize that equation I put on the last slide, we have A is equal to 46.53. Just a note that A, B, and C do have units. So again, based on consistency of units, the left-hand side is in degrees Celsius. And so every term on the right-hand side also has to be in degrees Celsius. So the units of A are actually also degrees Celsius. The units of B are actually degrees Celsius per meter, because you get a BZ term over here. So the meter and meter has to cancel out for the term to have a unit of degrees Celsius. And then C is actually units of degrees Celsius per square meter. So we see that B in this case is negative. That's an important thing to note in this case. We'll come back to it once we do further calculations. But B is negative and it has a value of minus 0.0628 degrees Celsius per meter. And then C has a value of, it's a very small value, and that's quite typical. It usually is a very small value, but with in certain exceptional cases, which we'll talk about later. C is equal to 0.0002 degrees Celsius per square meter. So pretty small number. Now, once we have calculated these values of A, B, and C, and because we are using a quadratic distribution where the neutral plane is our reference for the coordinate system, we can therefore use the formulas that I showed in the previous set of slides. That is from Ionides et al. As well as Kubani and Tia. And then we get these formulas for TC, TL, TN. And then using TN, we can go on to calculate sigma n. So we saw these formulas in the past. I don't want to rederive a lot of these formulas, but we saw them. And now we have A, C, B. And as you see, everything in this formula depends on ACB. There is one note here that we have an E and an alpha and a nu. So our problem, if I actually go back to the beginning of the problem, I never actually specified any material properties. Now, in analysis, that would be a strange thing to do. But in design, that's basically exactly what happens, that these values are not specified. So it's important for you as an engineer to be able to know what are some typical values for these properties. So in general, in design, you won't know the exact values of whatever we are trying to calculate a priori. You're going to have to make some assumptions. And then later on, the assumptions can be checked to see whether any significant deviation from the design happened. So in this case, we are not given E, alpha, and nu, which we need to calculate these eigenstresses. So we're going to make some assumptions and reasonable value assumptions on what they are. Okay, so we had this calculation that TC is equal to A plus CH square over 12. You will note A is a constant, C is a constant, H is a constant. Also, okay, one correction I should make, this B is degrees Celsius. I wrote degrees Celsius per meter, but we're actually fitting the curve to H. So, and H was in millimeters. Or Z was from minus H over 2 to H over 2, and H was in millimeters. So I should just make a correction. This is degrees Celsius per millimeter, and then C is also degrees Celsius per square millimeter. So please make that correction in your notes that this is millimeter because we took our length units as millimeter. So we had ATC is equal to A plus CH square over 12. All of these are constants. A, C, and H are constants, which means TC is going to be a constant, which is exactly what we expect. It's a constant component. TL is T naught plus BZ. By the way, we never talked about what T naught should be. We are simply going to use T naught is equal to 0 degrees Celsius. When it comes to calculation of stresses, it's not going to make a difference. So we'll just assume T naught is equal to 0 degrees Celsius so that the mathematics is a little bit easier. You will note that this is a function of B into Z. So TL is a linear function of Z, which is exactly what we expected since it's a linear component. And then we have Tn is equal to T naught minus CH square by 12 plus CZ square. So you'll notice Tn, T naught is a constant, CH square over 12 is a constant, CZ square is a quadratic term. So Tn happens to be a quadratic term. And then sigma n, which is what we're going to use to calculate our eigenstresses, is Ce alpha over 1 minus nu. All of that is a constant, into h square over 12, which is a constant, minus z square, which is a quadratic term. So here again, sigma n is basically going to be a quadratic distribution, which is also exactly what we expected. Okay, so now that we have A, B, and C, now that we have all of these formulas, by the way, the only reason we had these formulas is because we assumed a quadratic distribution, and so we have pre-computed formulas to use. If we did not do that, we'll talk about that towards the end of this example, what are the options we have to solve this problem. Anyway, given all these values and plugging them in over here, you get these expressions for assuming T naught is equal to 0. You have these expressions for TC, TL, and Tn. So and here you can simply put H is equal to 200 mm. Note the units. We fitted it against an mm, and so we have to continue to use mm. Do not change units midway through the calculation. So when we did that, we get these expressions. And then what I've done is I've actually plotted these values to give you an illustration of what the final solution looks like. So on the x-axis here, I've got z. Again, this is from the mid plane. So it's going to go from minus 100 to plus 100, keeping in mind that we did make some extrapolation. And on the y-axis, I've got temperature. Now, I've actually plotted all 4 of these temperatures. The first temperature which I've plotted is T. And in this case, what you'll notice is it goes from minus 100 to plus 100. So this is not the raw data. This is the fitted data, which then I've done a little bit of extrapolation to. So you'll notice the extrapolation is actually between these 2 points here and these 2 points here. So that's why a little bit of extrapolation has happened. Generally, it turned out to be a fairly smooth solution. So at least visually, I don't see any problem with having done that extrapolation. In general, you should be a little bit careful when you do extrapolation. Don't be sure that it's always going to be correct. But in this case, it seems to have been fine. So this is our fitted data for T. So this blue line over here was T. Now what I have is I have this orange line over here. This is just a flat line because it's a constant value with respect to Z. So it's just a flat line. This was TC. As it turns out, if you substitute these values in here, TC works out to 47.2 degrees Celsius. Quite a high value if you think about it. So what's that saying is that if the reference temperature of the pavement was 0 degrees Celsius, then the temperature at which the pavement actually is for the given temperature distribution, the uniform temperature distribution that the pavement acquires is 47.2 degrees Celsius. That's a big jump from 0 to 47.2. And then that's the amount by which the pavement is going to try to expand. So we have here this delta T in this case is Tc minus T naught. Since T naught is 0, delta T is 47.2 degrees Celsius. And so if you wanted to calculate the amount of strain, that is going to be alpha delta T. And then that's the amount that the pavement is going to expand because the temperature is increasing. So this is the strain by which it's going to expand. If I wanted to calculate the length of expansion, I can multiply this by the width of the slab. So I can say L or delta L is alpha delta T into capital L, where L is the width of the slab. And this will give me the amount of expansion which took place. It can be a fairly high value. However, in this case, there is no stress. We are mainly aiming to calculate stress, not the amount of expansion. There is no stress in this case because we generally assume that the base friction is negligible. So this is the amount of expansion that the pavement wants to make and is also free to make. So because the pavement is free to make this amount of expansion, there is no additional stress from this component. Now, the third line here is TL. That's what I've shown in gray over here. It's a straight line, as you would expect, because it's basically just a function of Z. So it's a straight line, and this is what we have the plot over here. You will notice that in terms of magnitude of T, it's actually really, really small. A vast majority of the temperature effect is actually just going into this TC. It's a relatively smaller amount which is going into TL. And what you see here, TL is varying from this value over here. We'll look at the exact numbers in the next slide, but it's varying from a positive temperature value to a negative temperature value. It's not always necessarily the case that it should be like this, but in this case, it happens to be like this. So what does that mean? If I try to plot the shape of my slab qualitatively, then I have a positive value on the top. So the slab on the top surface is going to be expanding, and I have a negative value on the bottom, which means with reference to the reference temperature, which is 0 degrees Celsius, the slab on the bottom is going to be contracting. So my slab actually wants to take this convex upward type of shape, which is generally what we would expect also. Again, this was a condition where we had this temperature was taken sometime during the day. And during the day, as we talked about in one of the earlier slides, this is generally the sort of shape that we expect. So this, at least qualitatively, this seems like a reasonable solution that we have gotten. And then finally, we've got Tn, which is the non-linear temperature distribution. You will notice that it's shown in yellow over here. It's a little difficult to see because it's compared to the other components. It's a pretty small value, but nonetheless, it is there. And so it is this component over here. What you will notice is that it actually has a positive value on either end. It looks like it is 0 at the origin, but at the midplane, it's not actually 0. It's a small value, and when we do our calculations for stress, it's not going to be a negligible stress, but it will be a small stress. So it's not 0 at z is equal to 0. It's just a small value at z is equal to 0. and it have a small negative value, I should add, and then it happens to have some positive value at z is equal to plus or minus 100. So these are the plots. What I want to point out again, the main important thing to look in this plot is a large amount of the temperature effect is actually simply going into into this constant temperature distribution. So the expansion and contraction, although we don't consider it in our calculations for stress because the base friction is generally assumed to be very small, but a very large amount of this expansion is actually a very large amount of the temperature effect is simply going into expansion and contraction, and it is a much smaller part of this component which is going into curling and eigenstresses. That's an interesting thing that's worthy of keeping in mind. Okay, now in this case, to go a little bit deeper into the numbers, if we consider the linear temperature distribution, which was shown over here, what we have is the value at the z is equal to 100 or minus 100, which is the surface, and the value at z is equal to plus 100, which is the bottom of the layer, that's the interface with the base layer. We have a temperature of 6.28 degrees Celsius and minus 6.28 degrees Celsius, respectively. So in this case, we actually have a symmetric distribution. The value is naturally 0 at the origin. So if we calculate the temperature difference, so what this value I have over here at the top, this I can write as Tt is equal to 6.2 degrees Celsius. And this value at the bottom I can write as Tb. What we are interested in for curling is not the actual value of the temperature, but the difference in the temperature. So we are interested in the linear temperature difference of this equivalent linear temperature distribution. And that linear temperature difference, delta T, by definition, I keep in mind again, this is the actual definition. Don't confuse yourself when you're looking at these numbers. It is top minus bottom. It is not bottom minus top. In theory, it could be bottom minus top, but by convention and all the other formulations also based on this assumption, it is top minus bottom. So in this case, it's 6.28 minus of minus 6.28, so that becomes plus. Add the two and you get 12.56 degrees Celsius. This is actually not an unreasonable value for temperature difference. Much later, will be several lectures from now, when we go into module 4, and actually halfway through module 4, when we start looking at IRC 58, which is the Indian design standard for rigid pavements, there again we'll actually see a very similar number to this. It's 12.56, we'll actually see a number 12.5. So that is a design value which is used. We'll see more details when we get to that point. But this 12.56 is actually a fairly reasonable number. It's not a particularly low or a particularly high number. So for Indian design applications, we are mostly fine with this delta T, which is sometimes called the linear temperature difference, or LTD. Now, in some applications, particularly related to US design procedures based on AASHTO, which again we'll look at in the first half of module 4, this temperature difference is sometimes also divided by the thickness to get what is called the equivalent linear temperature gradient, ELTG. This ELTG is an important acronym. You'll find it in many scientific applications in the literature. So it's basically this delta T, this temperature difference, which again is T top minus T bottom, divided by the thickness of the slab H. That then, for this particular application, it gives us a linear temperature difference of 0.0628 degrees Celsius per mm, which by the way is also the same value as B, which we had evaluated previously. So in this case, what we get for this particular problem that we're given with this data, that the linear temperature difference is 12.56 degrees Celsius. That's basically what we need for the Indian design standard. For the North American or AASHTO design standard, we actually need this equivalent linear temperature gradient. And so we just divide by H and we get this value. Note, it is called equivalent linear temperature gradient because this is the equivalent linear temperature distribution, which is a component of the overall nonlinear temperature distribution. So the name itself implies a certain procedure has been used to calculate it. We had looked at this before, but just to reiterate, you will notice here that delta T is greater than 0. That's what we expect because we expect the pavement to have a shape as I'm drawing over here. So the top surface is expanding and the bottom surface is contracting relative to the neutral axis or relative to neutral plane. So this is probably a daytime temperature distribution. And this also happens to be a case of bottom-up cracking. So if I apply a load over here, the constant component is basically not causing any stress because we assume that the base friction is negligible. So push that aside. But if we consider curling, And when the pavement is trying to assume this sort of a shape, again, this is not the actual shape of the pavement. It's the shape that the pavement is trying to assume. It is going to be restrained, of course, by the self weight, but also by an external load which may be applied over here, as I've shown. In this case, the bottom surface, this little point at the bottom fiber, is actually being pushed apart. As the slab is being restrained, this bottom surface is being pushed apart, and therefore it is under tension. So we actually have tension here at the bottom. Again, concrete is much more stronger in compression than in tension. So largely, we are very concerned about the tensile stress. We are not very concerned about the compressive stress. We do actually have compression at the top. It will be an equal amount, but opposite sign of compression at the top. So we're not particularly concerned about the compressive stress. We're concerned about the tensile stress, because it is at this point, once the tensile stress exceeds the strength. Actually, that's not what will happen. It's based on repetitions and fatigue theory. So we'll talk about that in module 4 much later. But what will happen is, because this bottom surface is at tension, eventually we're going to have a crack that starts to form. So it will start at the bottom, it will propagate upwards, which is why this is called bottom up cracking. So this particular example which I'm showing, this could lead to a case of bottom up cracking forming under certain conditions of fatigue, which we'll talk about in module 4. But let's also now consider the eigenstress. So this bottom of fatigue discussion which we had, this is purely based on the concept of curling stresses. So when I said this is a tensile stress over here, that's a tensile curling stress. So now let's look at the eigenstress, because that's an additional contribution that we have. The formula for eigenstress, it's what's shown over here. It's E alpha into 1 minus nu Tn of z minus T naught. We can already substitute the values. We have Tn. We could just substitute Tn in terms of A, B, and C, which we had previously. Substitute in the values, and you'll notice this negative sign over here. The negative sign says that tension is positive. That's the basic reason it's added to the formula. That if we have a positive value, then the tension is positive. So if we have a negative value of the stress, that's a compressive stress. Now, here again, in order to calculate this, we need E alpha and nu. We were not given those values, so we need to make some reasonable assumptions. In pavement engineering, a reasonable assumption is that E is equal to 30 gigapascals. We looked at this before. Please go back to module 1 in our lecture on material properties, and I showed you that 25 to 30 gigapascals is not a bad assumption. Nu is equal to 0.15. Again, pretty decent assumption for concrete. Alpha we may not have looked at before, but generally a good value for concrete is 10 to the power of minus 5 per degree Celsius. So note the units. I hope you studied this in high school. Sometimes you find this written as 10 into 10 power minus 6 per degree Celsius. Same thing, 10 power minus 5 per degree Celsius. So these are typical values. You will note generally we want our stress to be in megapascals. And so what we would like is, we would like E to also be in megapascals. So actually the value of E we use here should be in 30,000 megapascals. We generally don't report the stress in gigapascals. We report the modulus in gigapascals, but stress is generally shown in megapascals. So we have to take care of that unit conversion. I hope by now you are all familiar with doing this unit conversion. So if we do that, what I've plotted over here is, along the x-axis, again, I've got z, the z coordinate, which is on the midplane. So it goes from minus 100 to plus 100. That's from the surface to the interface with the base layer. And z is equal to 0 is the neutral axis. And then I've plotted the eigenstresses in this diagram. What we will see here is we do get a parabolic sort of shape. That's actually quite expected. Our original distribution was parabolic to within 99.75% of variance. Our original distribution was parabolic. We decomposed it into some kind of a rectangular or constant distribution, a linear distribution. So whatever is left has to actually be parabolic, so that when we sum them together, we recover a parabola. So in this case, our eigenstress is parabolic in nature. And then what you will note, as I've put on the next slide, you will note that we actually have, in this formulation, a positive stress refers to tension. That's why we have this negative sign over here. So positive stress refers to tension. What you will note is that the maximum tensile value of the eigenstress is actually coming at about 0.23 megapascals at the midplane. So this is where we're getting the maximum positive or the tensile value, which I've written over here. So that's the maximum tensile value is not coming at the top or the bottom face. It's actually coming at the middle, which is on the neutral plane. At the top and at the bottom, we actually have a compressive stress. which happens to be equal to 0.47 megapascals. That's both at the top and at the bottom. So that's the value which I have over here. So it's a compressive eigenstress with equal value at the top and the bottom, and it happens to be compressive in nature, equal to 0.47 megapascals. That's what the negative sign indicates, that it's a compressive stress. Okay. So what does that mean in terms of the overall stress? Again, this is the shape that our slab wants to take under purely linear temperature distribution. It is not a purely linear temperature distribution, but if it were purely linear, then we're simply going to put a load over here, and we're going to have tension at the bottom, and we're going to have compression at the top. That's what we get when we only consider curling. But now when we also add eigenstress, then what we see is that the top surface has a compressive curling stress over here. We already saw that. And it happens to have a compressive eigenstress. So the compression caused by curling is being added to by the compression of the eigenstress. So our top surface is under a higher value of compression. That's perfectly fine, because generally our compressive strength is very high for concrete. Our bottom surface in this case is actually tensile in curling. That's this T which I've put over here. So our bottom surface is in tension under curling, but the eigenstress is compressive at that point. That's 0.47 megapascals. So what we are getting here is that the bottom surface consists of a tension stress plus a compressive stress. Then the tension is going to be positive, the compression is going to be negative. So net, we are actually reducing the stress at the bottom surface. So in this case, what we see is that if we ignore this compressive eigenstress component, we would actually overestimate the tensile stress at the bottom of the slab. In this case, the eigenstress is actually reducing the stress at the bottom of the slab. We would be doing an over design if we did not take this into account. Now, this happens to be for this particular case. It is not the case all the time. It is possible that during the evening, during the night, during early in the morning, you have some other types of distributions which can generate a situation where you have fairly high eigenstresses at the top or at the bottom. And so then these results change. So I don't want you to think that these are universal results, that this is how all pavements behave at all points of time. This is the result for this particular example that we're solving. We have to look at other examples in order to get our results for different situations. Now, one last note before we conclude this example. We did a quadratic fit in this case, and we saw that in this case, 99.75% of the variance, which is for engineering purposes, that's all of it, almost all of the variance was accounted for by our quadratic fit. So this was a perfectly fine approach. Sometimes it doesn't work. Depending on the type of distribution, depending on when it was collected, sometimes a quadratic fit may not be that good. In which case, the next idea is you can use a cubic fit. From my experience, a cubic fit is the best one you need. Beyond a cubic polynomial, you generally don't need such high order polynomials. So quadratic will work in most cases. Cubic is also okay if quadratic is not good, if the R square is not high enough. Generally, with cubic, your R square will perfectly be fine. Now, maybe I actually haven't come across a situation, but in some situations, even a cubic fit might be poor. And actually, there is one situation where that is the case, that is the shrinkage distribution. This is piecewise linear, and there is no way a cubic fit is going to do a great job at approximating a piecewise linear approximation. So when you have shrinkage, our fictitious shrinkage temperature has this triangular distribution, and there's no way this is going to be cubic. So in this case, it is actually best to perform some type of numerical integration or quadrature to get this. So if it's difficult to fit it to a nice polynomial and perform an analytical integration, then it may be necessary to perform a numerical integration. One such method could be trapezoidal rule, and I hope all of you have studied that. If not, you should take a class on numerical methods and just learn what is trapezoidal rule, Simpson's rule, etc. Okay, so with that, we conclude example 1. That was the largest example I wanted to go through. Example 2, I'm going to go through it quickly because it's just applications of formulas. There's not really too much insight to be gained, but we should know how to apply the formulas. Example 2 is going to be based on shrinkage. In particular, we are going to use the Bajant and Baweja B3 model. Okay, so the question is as follows. An M40 grade concrete. So note, we are given M40. I am assuming most of you are civil engineers, so you've seen this notation before. M40 is just a way of saying that the compressive strength is 40 megapascal, or rather the characteristic compressive strength is 40 megapascals. So we have this FCK is equal to 40 megapascals. And note, we always choose a system of units. So we generally take Newton per mm square. So we take Newton as our unit for force, mm as our unit for length. Newton per mm square happens to be equal to megapascal. So here we don't have to do any unit conversion. We have FCK is equal to 40 Newton per mm square. Okay, so let's go back to the question. An M40 concrete slab is to be constructed in a region with an average relative humidity of 40%. Now, this is it doesn't have to be the year-long average. It can just be the average during the period of construction. The slab will be cured with moist jute bags. So if you recall from our previous lecture, we have several ways of curing. Well, we could not do any curing. That's one option. It's a bad option, but it's an option. We could do curing using these jute bags. That is, we have these wet jute bags. We place it over, and then we make sure the surface remains moist. We get a lot of variability in this case, but it's certainly an option. Another choice of curing would be using a curing compound, where we're using a chemical to lock in the moisture and prevent those moisture gradients from forming. Another option, for example, could be steam curing, but for pavements, generally not used. So the slab will be cured with moist jute bags. The water content in the mix design is specified as 300 kilogram per cubic meter. Again, I encourage all of you to, certainly those of you who are civil engineers, to take a course on concrete technology. You'll see how these mix designs are done. But generally in a mix design, we specify what is the weight. So mix design is done volumetrically. We specify that for 1 cubic meter of concrete, what is the weight of different components to add. Cement being one of those components, or water being one of those components, we are given that the water content is specified as 300 kilograms per cubic meter. We are given TC is equal to 3 days. TC is the time of curing, which means that when these moist jute bags which are applied, they're applied for 3 days in this problem. That's also fairly typical in actual practice. We saw this before tau SH. This is some characteristic shrinkage time. It's actually the time over which half the shrinkage strain has been gained. And as such, the number has to be calculated using somewhat complicated calculations. It's related to the morphology and the type of concrete crystalline structure that we gain. But in general, we can simply assume that tau SH is equal to 35 days. Very common assumption made in pavement engineering. So we assume that tau SH is 35 days. The question is, plot the shrinkage temperature distribution. That is, what is the equivalent temperature distribution that's causing that maximum strain? Plot the shrinkage tension distribution TSH as a function of time over various days. I should keep in mind this shrinkage is only going to begin after TC, because from 0 to TC, we basically are covering the surface with water, so we don't have a moisture gradient. So we don't start the shrinkage over there. The shrinkage starts only after 3 days. And so we will be starting this plot only from T is equal to 3 days. Okay, we saw a lot of the formulas over here. So we are going to use the Bajant and Baweja B3 model. We saw a lot of the formulas, so I'm not going to actually repeat too much of the calculation. I just want to show you what a reasonable solution looks like. This was the basic formula which we saw, that basically we need this epsilon SH infinite. So this is the shear, this is the strain. Actually, it's a normal strain, not a shear strain. This is the normal strain due to shrinkage at infinite time, that after a very long period of time. We saw that this is a function of some ES infinity, it's a parameter, and some correction factor for the fact that the elastic modulus is also changing with time. So this is going to be the elastic modulus at 607 days to the elastic modulus of TC plus tau SH. We note that TC plus tau SH is 3 plus 35, so that makes 38 days. So the first thing we have to calculate is, we need to calculate this ECM 607 and ECM tau C plus tau SH. We are given this formula in the ACI document, that ECM at any time t is ECM at 28 days into this nonlinear function of t. ECM at 28 days, since it's not given to us, we have to estimate it. We can estimate it using this formula. So it is some value, some constant, into the square root of FCM at 28 days. FCM at 28 days is that M40 which we used. So we simply substitute 40 megapascals over here. Now, one point to note, you have, when you're using an empirical formula like this, you have to be pretty careful with the units. You actually have to read the formula, the definitions below the formula, and check which units are these. This formula says that FCM has to be in megapascal. So this FCM over here, which is FCK in our Indian notation. So this has to be in megapascals. And the E which comes out of this is going to be in gigapascals. That's what the formula is derived as. So be very careful not to do any inappropriate unit conversions in an empirical formula of this nature. Okay, so when we plug this in, we get an ECM at 28 days of 29.94 gigapascals. Pause, you should realize and ask yourself, is this a correct answer? Does this look reasonable? In the first example, we had taken an assumption of 30 gigapascals and we said that that's fairly reasonable based on measurements. So in this case, we have 29.94 gigapascals, almost 30 gigapascals. So this number also seems to be appropriate. So always don't just solve this mechanically. Remember, you are engineers, you're not mathematicians, with all due respect to mathematicians. But make sure that you look at the numbers and ask yourself, are these correct? Do these look correct based on my engineering knowledge? Don't just hope that the mathematics is getting you the right answer, because it's possible that you can make mistakes. Okay, so now because we have ECM 28, we can calculate ECM at any time t. So this correction factor, when you just substitute the numbers over here, I'm not going to go do all the details for you, we will get this correction factor is 1.0560. So now we have this term over here. We have to calculate ES infinity. ES infinity is calculated using this empirical formula. This is minus alpha 1, alpha 2 into 0.019 W. W was the water content. This has a unit of kilogram per cubic meter. That's how it's been defined. That's how this empirical formula has been calculated. Alpha 1 and alpha 2. For alpha 1, we assume that we have type 1 cement, fairly common assumption. So alpha 1 is equal to 1. And alpha in this case, it is cured using 100% relative humidity, which is just a way of saying that we are keeping the surface moist. So this is moist curing, and that's why the table says that alpha 2, sorry, I'm missing a 2 here, alpha 2 should be equal to 1. W we are already given as 300 kilogram per cubic meter. FCM 28 we already have as 40 megapascals. Note, don't do any unit conversions. This FCM is supposed to be in megapascals. W is supposed to be in kilogram per cubic meter. Don't change the units when you're using an empirical formula of this nature. Plus we've got 270, which is a constant. This then gives us that the solution, this entire term actually turns out to be very small. So finally what we get is epsilon S infinity is minus 270 microstrain. And then when we multiply it by 1.056, which is the correction factor we got from the last set of slides, last slide, we get this epsilon SH infinity is 285 microstrain. And then KH we can calculate previously, given H is equal to 0.4. KH we can calculate as 0.936. And so when we substitute the formula in, we get that this is the variance of the shrinkage strain. But usually we also write this in terms of the temperature. So using this formula, which we had derived previously, this is for a triangular distribution of the strain. Using this formula, we finally get that the temperature distribution with respect to time, the equivalent shrinkage temperature or the fictitious shrinkage temperature, is given by this formula, which I have plotted over here. What you will notice is 0 to 3 days, we don't use the formula. The formula only begins from t is equal to 3, because before that, we don't have shrinkage, because it's still under curing. And now we get a curve like this. And what we see is that at 90 days, so I've actually calculated this out all the way to 90 days. At 90 days, we actually get a delta T. So this TSH is actually an additional delta T, which has to be applied. This actually turns out to be 8.22 degrees Celsius. So in the previous lab, we had calculated delta T just from curling as 12.56 degrees Celsius. And now we see that if you include shrinkage in the calculation, you additionally add an 8.22 degrees Celsius. So you're going to go somewhere close to around 21, 22 degrees Celsius. That's a pretty high value. So you can see that the shrinkage strain actually can lead to quite a large amount of temperature difference, and that can lead to quite a large amount of stress developing. So that's why it's not a good idea to ignore it. It can be quite a significant value. Okay, so that concludes these examples. I hope you go through these examples. Take care. In some cases, you have to be very careful of units. In some cases, when you're using empirical formulas, we have to use the exact units specified by the formula. We don't try to use a consistent system of units. So it can get a little confusing, but I hope you practice the example which I've done. Please go through it yourself. In the next lecture, we will now start module 3, where we're going to look at the analysis of rigid pavements using the finite element method. And there we'll look at some techniques on looking at multi-layered rigid pavement systems. So I will see you in the next lecture. Thank you.